Okay, let's continue our class. We will discuss about functions with restricted domains. In the last class, we have discussed about uh, one-to-one function and the inverse function of the original function. Uh, the question is, given a function, if this function is not a one-to-one function, how can we get the inverse function? Because the inverse function may require the original function to be a one-to-one function. So, if given a function, if it's not a one-to-one function, it may be possible to restrict the domain to make it one-to-one function and hence find the inverse. Here we have some examples. Um, we just try to find out the suitable restrictions of the function x squared plus 6 over 7, and we try to find out the inverse, and we then sketch the function and the inverse function on the same set of axes. We will label all intersections. First of all, we will understand that x squared plus 6 over 7 is a parabola. When x is equal to 0, we just sketch it. We got y is equal to 6 over 7. We got y is equal to 6 over 7. And then we get this is the minimum number. This is the minimum value of this parabola. From the sketch, we may be able to get two one-to-one function by restricting the domain. The domain can be either x is larger than or equal to 0, or x is smaller or equal to 0. We just here first of all we just choose x is larger or equal to 0, which is the right hand side of the parabola sketch. This from the we can find out from the sketch that this is a one-to-one function. This is a one-to-one function. So in order to get the inverse, function, we just swiping x and y of the function with restricted domain, and then we just substitute x by y and substitute y by x. Then we will get x is equal to y squared plus 6 over 7, and the range will be y is larger or equal to 0, while the domain is larger or equal than 6 over 7. We just substitute x by y and y by x. And then we will get y is equal to square root 7x minus 6. It can be positive or negative. And this it can be positive or negative. Because y is larger or equal to 0, then we will get y is equal to square root 7x minus 6. 7x minus 6 square root. This is the inverse function of the original function. So f and y, the original function. Second, let's find out the intersections of the original function and the inverse function. We have fx is equal to x. And Do you still remember that what we learned from nursery class? In order to find out the intersections of the function as well as the original function, we needed to make sure fx is equal to x, and fx here is equal to x squared plus 6 over 7. It should be equal to x, and we have x squared plus 6 is equal to 7x, and we can do factorization. X minus 1 multiply with x minus 6 is equal to 0. And then finally we got x is equal to 1 and x is equal to 6. X is equal to 1 and x is equal to 6. Um, for in order to sketch, now we found two intersection points. We in order to um, uh, sketch the function as well as the the inverse function, we just sketch one and mirror it. According to the line y to x, y. Anyone who can tell me why is that? Because uh, the original function and the inverse function are what? Are reflections to the line y to x. Are reflections to the line y to x. Y to x. So, uh, so here we have intersections. X is equal to 1 and x is equal to 6. X is 1 and x, because we have fx is equal to x, so we got two intersection points are 1 1 and 6 6, and we can get when y is equal to 0, and we got x is equal to 6 over 7. We got a point here, and we also got think we can draw a line like this. And then we just mirror it to y is equal to x, to this line, and then we can get the sketches of both function and the inverse function. Uh, Here I give you another example. Another example. We want to find out the inverse function of the square root 10x minus 25. 10x minus 25. We have the range x is larger or equal to 5 over 2. We also have y is larger or equal to 0 as we have the domain x is larger or equal to 5 over 2, and the range y is larger or equal to 0. We can sketch the function as well as the inverse function on the same set of axes. Just swiping x and y, it will give x is equal to square root 10y minus 25. 10y minus 25. And finally, we got y is larger or equal to 5 over 2, and x is larger or equal to 0. Am I right? So we just square both sides, left hand side and right hand side. We've got x square is equal to 10y minus 25, and minus 25, and We just substitute x by y and y by x. Finally, we got um, y is equal to x squared plus 25 over 10, and we can also get the domain as well as the range. For intersections, we just calculate, and we just that fx is equal to x. Fx is equal to x. We then have x squared plus 25 is equal to 10x. Is equal to 10x. And because the sketch is and finally we found that x is equal to 5, and at this moment we understand that the point 5 is the intersection point. So let's come to, and we can sketch that when y is equal to 0, and we got x 5 over 2 for y for the function fx, and because we have the intersection point, we can draw a line like this. And as I mentioned, because the function and the inverse function are reflections to each other according to the line y is equal to x, we just map it, we just mirror it according to the line y is equal to x. Very simple, alright? Then we will go over limit. So what is limit? Given a function fx, if fx approaches a limit L, given a fx, if x approaches to a constant a, and then the fx will approach a limit L, also a constant or infinite. We can write it as we just say this function has a limit L. X approaches to a and fx approaches to L, we say the limit of this function is L. I'll give you an example. We have fx is equal to x squared minus 1 over x minus 1. This is not defined at x is equal to 1 because at this point the denominator will become 0, which is not allowed. But given the x-axis, x can approach to 1 and be very close, and get a value very close to 1 from the left hand side and the right hand side in the x-axis. For example, we go for the right hand side 1.01, which is a little bit slightly bigger than the value 1, and then we got y is equal to 2.1, and we can also calculate x is equal to 0.99, and then we can get a value of 1.99, etc. So note that y is equal to x squared minus 1 over x minus 1, because here we will do factorization of the denominator x squared minus 1. Normally we will get x minus 1 by x plus 1. Because x approaches 1 means x will not be 1 forever. So we can compromise x minus 1 from the denominator as well as the numerator. Then we can get a splitting function when x is not equal to 0 to 1. We have fx is equal to x plus 1, and when x is equal to 1, the function is undefined. The function is undefined. At this moment, we can get that when x approaches to 1, I emphasize that x approaches 1 means x will not be 1 but very close. So we can get the limit of the function x approaches 1 is equal to 2. Just the 2. Just the 2. We just substitute x by 1 and get 2. We can sketch it. Here there is a line, and x plus 1 is a line, but at the point and when x is equal to 1, it's undefined. We can go for another example. Fx is equal to x squared minus 5x plus 6 over x squared minus 3x plus 2. We found that the domain will be, we just do factorization like this. Fx will then become x minus 2, x minus 3 over x minus 2 upon x minus 1. Then we get when x approaches 0. We just it will become very simple. When x approaches 0 for this part, for the denominator and the denominator x squared will become 0. Minus 5x will become 0, and in the denominator x squared will become denominator, and minus 3x will become 0. X squared will become 0. Minus 5x will become 0, and this part will become 0. Only the remaining part indicates that the limit of the original function when x approaches 0 is 3. Yeah, is 3. We can also calculate fx when x approaches 1, because at this moment, according to the factorization result, x minus 1 when x approaches to 1, it will become 0. And in the above x minus 3, no matter what x minus 3 when x approaches 1, no matter what x minus 3 will give us, the limit will become minus 2 over 0. At this moment, because the denominator should not be an infinitesimal word, I think undefined. Let's come to the next example. Fx is equal to x minus 3 over x minus 1 when x approaches to 2. At this moment, we just substitute x by 2, substitute the x in denominator by 2, and we can get minus 1. And the next one, because we want to calculate the limit when x approaches to 3, but here is okay, the denominator is okay, but for numerator it will become 0, so finally the limit is 0. It's very simple, very simple. For infinitesimal, here we just give you a one shape from 3 to infinitesimal and from negative infinitesimal to 0. This is one tab. Here we can focus on the right hand side and the left hand side. Both of them are one-to-one function, but if you combine them together, they are not. They are not. So here we can sometimes, in order to help you to calculate the limit of a function when x approaches to a value, I think in this week we will tell you how to get it. But before that, we need to understand more about the limit. For example, here we have some formula. We have some formulas. Fa, given an example of given a function fa, if fa exists, and the limit of f(x) when x approaches to a should be fa. And if there is a form where fa has the form k over 0, the limit of the function will be undefined. If in the function, if the function has the form 0 over 0, at this moment, it's better to be evaluated by factorizing x tends to 0. X tends to 0. Here we can give you some example. The first example is about x squared minus 6x plus 2 or plus 7 and x squared minus 3x minus 4. We calculate the limit of this function when x approaches to 4 or approaches 4. Now we just it's very easy. From 4 we just calculate. We just substitute x freely by 4, and we can get the result directly. And secondly, we have the calculation of the limit x squared minus 9 over x minus 3. For this case, where x approaches to 3, you just here x approaches to 3 means it won't be equal to 3. We just compromise x plus 3 from both denominator and as well as the dominator, and then finally we got result to be the calculation of the limit of x plus 3 where x approaches 3. Finally, we got the result 6. We got the result 6. Okay, that's all for the third class. That's all for the third class.